Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. The moon is often described as airless, lifeless, and still. But in 2024, scientists revealed that this silent world is not so lifeless after all. At least, not in terms of activity at the atomic level. Using advanced isotope analysis on Apollo-era lunar samples, researchers made a breakthrough discovery. Meteorites, not solar wind, are the primary source of the moon's thin atmosphere, or more accurately, its tenuous exosphere. This discovery not only solves a long-standing planetary science mystery, it also reshapes our understanding of how airless bodies across the solar system interact with their cosmic environment. Why? What kind of atmosphere does the moon even have? First, let's get clear. The moon doesn't have an atmosphere in the way we experience it on Earth. Instead, it has what's called an exosphere, a ghostly cloud of atoms so thin they rarely collide with each other. This exosphere is billions of times less dense than Earth's atmosphere, but it's there just enough to measure. For decades, scientists debated, where do these atoms come from? Two main theories competed. Solar wind sputtering, where charged particles from the sun slam into the lunar surface and knock atoms loose. Meteorite impacts, where space rocks hit the moon and vaporize material, sending atoms flying upward. Until now, no one knew which was dominant. The breakthrough: decoding ancient lunar dust. In 2024, a team of geochemists revisited Apollo 17 samples using modern ultra-sensitive mass spectrometry. They looked specifically at isotopes of potassium, K, and rubidium, Rb, elements that are relatively volatile and sensitive to heat-driven processes. What they found was striking. The heavier isotopes were enriched in the soil, suggesting that the lighter isotopes had been vaporized and lost to space. A classic fingerprint of impact vaporization, not solar sputtering. This allowed them to quantify the relative contributions for the first time. 70% of the exosphere's atoms come from meteorite impacts. 30% come from solar wind gardening. This not only settles the long-standing debate, it adds a new layer of dynamism to the moon's story. The moon, a constantly bombarded world. Meteorites don't just hit the moon occasionally. They do so all the time. Without a thick atmosphere to burn up small space rocks, even tiny meteoroids strike the surface at high speeds, turning rock to vapor in an instant. These impacts don't just blast craters. They also inject atoms into space, forming a short-lived cloud that hovers above the surface. This vaporized material eventually escapes into space or settles back down, meaning the moon's exosphere is constantly in flux, changing with every meteor shower, micrometeorite burst, or even human rocket landing. This vapor loop explains mysterious exospheric spikes observed by instruments aboard LADEE, Lunar Atmosphere and Dust Environment Explorer, in 2013, and predicted how future lunar operations might disturb the environment. Why? It matters for exploration. The moon is no longer just a scientific curiosity. It's a destination. With missions from NASA, China, India, and private companies now landing on or preparing for long-term lunar operations, understanding the moon's environment is critical. Every landing, every drill, every rover kick-up sends dust and atoms flying. And now we know that such activity feeds the exosphere. This has implications for habitat design to minimize contamination. Scientific instrument, calibration, space weathering prediction, radiation, exposure modeling. Knowing that the exosphere is mostly meteorite-driven helps scientists better model how dust and gas move near the surface, vital for future observatories, telescopes, and astronauts working in situ. Beyond the moon, a universal process. The moon is just the beginning. Similar exospheres exist around Mercury, the asteroid Bennu, Jupiter's moon Europa, and Saturn's Enceladus. In each case, space weather, especially meteoritic bombardment, plays a role in liberating surface atoms into space. By understanding how the moon works, we can apply those lessons elsewhere. Mercury's exosphere is dominated by sodium atoms, likely from micrometeorite sputtering. Europa's thin oxygen atmosphere might be sustained by bombardment and surface chemistry. Even Enceladus plumes may be shaped in part by surface impacts, not just subsurface vents. This makes the moon a template for comparative planetology, our nearest analog for understanding airless worlds and how they breathe, the legacy of Apollo. And perhaps most importantly, this discovery is a reminder of the power of sample return science. These results came not from a new mission, but from decades-old Apollo soil. New tools, new perspectives, and smarter questions unlocked a secret that had been hiding in plain sight for over 50 years. It speaks to the importance of archiving space materials, funding planetary labs, continuing long-term scientific analysis, because sometimes the most profound answers lie not in what we haven't seen, but in what we're finally able to understand.